Hello everyone, we're going to start talking about where we left off in chapter 3, but I'm just going to go right through the chapter really quickly until we reach where we were. So chapter 3 is about making decisions. It's about if statements and dealing with different kinds of conditions that are actually going to lead to Boolean expressions as well as relational expressions like less than, greater than, and so on. So we looked into the if statement, just reminding you. So if statement actually takes a condition, and that condition can be based upon all kinds of information. It doesn't have to be just a single condition statement. And then depending on whether that condition returns true or false, you do one thing or another thing. So I'm going to also show you other details on this, again, just quickly, because we have done these things in classroom already, so I don't want to spend the time to do it again. An if statement in general is like this. You have if condition, then a list of statements. Again, it doesn't have to be a single statement like this one here. It would have all kinds of things. Then we have else. This is the simplest form. And we're going to see, I'm skipping these because we looked at these already. So we have to be careful about the indentation, as we mentioned. So we can actually write things in more detail. So the simplest form is like this, as I said. So you have if and then else. We can write this in short form as well if what we have is just an if else. So in that case, we have value 1. That's the result of that's going to be returned if a given condition is true. Otherwise, another value. So instead of writing, actual floor is floor minus 1 if floor is larger than 13, else floor. We could write this long statement, which is the same thing, but we don't have to write it, as long as this, we can just write it on a single line. It reads a lot simpler anyway. And we can just say this is the result of if floor is larger than 13, which is floor minus 1. That's what we're going to return. If that's not the case, then we just return the floor value, and that's it. So this general pattern is, something we can use in a lot of places, so it's quite useful. So the general format, actually, I think I have it in my notes, but I wanted to mention that is besides doing an if else, we have if else if else if else if else if else if, whatever many we need, but of course too many means that we're not doing it right. And then finally ending the whole statement with an else. Next is relational operators, which we looked into. So these are less than equal to, greater than, greater equal to, or not equal to. So there we go. That's the whole list. So the Python notation is what we need to remember. So the other thing is, we mentioned the fact that we should never use equal with floating point values, since the internal representation of floating point values is never exact. But we can use these things, of course, with integer-based values like characters and regular integers. So another thing is that when we are comparing strings, we mentioned that we're actually going to be using the ordinal value or the ASCII value of each letter. So lowercase and uppercase matter. So the lowercase W is not the same thing as uppercase W. They're two different letters because they have two different values. So we can go through these things. We did all this stuff. So we talked about this exact comparison because I'm going to switch to my notes, so we'll talk about these things once again. Strings are compared based upon their lexicographic ordering, which means alphabetic ordering. So we go, character by character, and then if we can make a decision, we stop. If we cannot make a decision in the case of less than or greater than, it means, we, as long as we have equal values, we keep going until we find something that's not equal. And so let's move on. We have talked about this as well. So what I advise you to do is just run through all these programs, run them yourselves, and make sure that you understand exactly what's going on. We cannot go through these things in lectures in detail because this book is really detailed, which is nice, but that's more for you to actually process than for us to talk about to that extent. So please read all these things really carefully and try to solve as many exercises as you can in the book. Check, double check. I'm here for you, to help you. So, and then we talked about nesting if statements. We can, nest if statements under other if statements. That's not a problem. Like this one here, if marital status equal to S, then you can have another if statement inside. You can have other if statements anywhere actually. So we have an if statement in the else part, another if statement in the if, in the main if part. So we can do all these things. So again, hand tracing is critical. This is what I've been talking about as far as manual or on paper checking, on paper working, which is something that you should keep in mind and do all the time. So if we have multiple alternatives, then we have to keep checking and keep checking and keep checking. Of course, we're going to see better ways of doing this, because this is very difficult to read and understand for others as well as for us actually. So there's a way to rewrite these things, but if we end up having way too many of these if statements, then there are other ways of doing the same thing without creating a lot of confusion. So, and I'm moving on. So, sending an email is something that you can take a look at. You're not going to be responsible for that. So take a look at that on your own to learn. Okay, so we talked about flowcharts. I'm not gonna run through these again. So, and I think we're coming up close to. We also looked into this case, and I think we're right here. So, Boolean values and operators. So we have Boolean expressions. We have so we have everything that evaluates to true or false. So, so I'm going to talk about more, about this in my notes a little bit more. But if you take a look at this table, we have A and B, so we have all the possible, combinations of values: true, 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 false, false, true, false, false. A and B would get you true for true, true only. Anywhere else, we have, a single false would get false. And A or B is going to result in a true as long as you have a single true value. So we have 3 trues in the first 3 rows, and we have false when we have false, false. And not A is, of course, just the reverse of what we have. So now the book is saying that, right here anyway. So we can check if the temperature is less than or equal to 0, or temperature is larger or equal to 100. If that's the case, we don't have it, liquid, because it's either frozen or it's in gaseous form. So so sometimes we need to invert. So we can say, not something in the case of if not frozen, then it's actually the case that it's not frozen. So we can take a look at all these conditions. So we can take a look at this program. We need to enter a number, a floating point number, X and a Y, and then we check if they are the same. Of course, as we said, this is not a good idea. We can check larger, so X is larger than Y. We can check if X minus Y is between is within a range. Again, checking for equality is dangerous. So we may get good, we may get the correct result, but that's not something that we should depend on. So now we need to be really careful and just pay a little attention about how we can convert regular English statements into Boolean expressions, so we can express exactly what we need to in order to uh, create a program that would solve the problem at hand. So if we take a look at some of these statements, like you were never married, how would you check for such a thing? That you are legally separated or divorced on the last day of the tax year. So this is a loaded statement. First of all, you need to check for being legally separated, and then check for divorced, and check for the date being the last day of the tax year, and so on. So we'll take a look at these as well. So the child lived in your home for all of the tax year, so you need to define what the tax year is, from what month to what month, and you need to check that your child has lived in your home during that time. So readability is actually something we need to pay a lot of attention to, and the book suggests that you should never compare against a literal Boolean value, which is true or false, in a logical expression. So you should never do if frozen is false, which means it's not frozen. If frozen is false, instead do if not frozen. Okay. Next thing is chaining relational operators. Unlike in other programming languages, we can write nice mathematical looking expressions, relational expressions in Python. So if a value has to be between 0 and 100 inclusive, we can just write it like this: 0, so value being larger or equal to 0, or being less than or equal to 100. So we don't have to separate the conditions like this. We can just write them in a single statement. So this is considered a single statement. It's a lot easier to understand because that's how you would actually represent this kind of a relationship in math. So it's just one-to-one. So we can also write other chained relational operators like this: a less than x and x being larger than b. These are exactly what I just said. But you can just combine it and then have it in a single expression. Now, Boolean operators are actually evaluated in a way such that as soon as you are able to decide, you stop. Meaning, if we are checking for quantity being larger than 0 and price divided by quantity being less than 10, if we have a decision that we can actually extract out of the first condition here, we just stop. So if quantity is 5, for example, then 5 would be larger than 0, then you wouldn't actually check. That's what short-circuiting means. You wouldn't check the remaining condition. So we just decide here and then never look into this other portion. So that's what short-circuiting means as far as the evaluation of Boolean operators are concerned. So De Morgan's laws are something that you guys have to know really well. We can go through some of these things, but take a look at the whole thing, because I think the book doesn't cover everything here. But anyway, it's just a nice reference here. So if you have something like this: if not, country is equal to 0, or state is not Arkansas or Alaska, I'm sorry, and then state is not Hawaii. So this could be confusing, but as you know, not A and B is the same as not A or not B. So when you have not, you not the operands, and you inverse the operator inside a parenthesis. So if you have not A or B, then this would become not A and not B. So if you have not state equals to Alaska or state is equal to Hawaii, it means state is not Alaska and is not Hawaii, because actually, so trying to understand it like this, it's a bit more difficult. That's what the book is saying, and it's actually right. But you can write it like this. It's the same thing as this, which means state is not Alaska and state is not Hawaii. It's a little easier for us to understand. But we can write it like this, but we should know that this is the same thing as this, or this is the same thing as that. So we can actually separate it up like this. So if you have not country is equal to United States and state is not Alaska and state is not Hawaii, we can actually separate these things into three, since we have three relationships here. So I can say not country equal to USA, but then since we are actually taking out the AND operation here, we need to convert it to an OR because we have not outside. But we are not in the condition, so we have that, or not state not equal to Alaska, or not state equal to state not equal to Hawaii. But you know, we have not and then not inside in these two, so we can just actually convert those back to equal. So country not equal to United States because we have not outside, but state not equal to Alaska. The not outside would be state equal Alaska, and the same for Hawaii. Okay. So some things about strings. So checking whether a substring is in a string, and again, remember that a single character string is still a string, and multi-character string is a string. All of them are strings. We don't have any difference between a character and a string. A single character is a string of length 1, so it's still a string. So this is, so we use the in operator for checking this. So we check whether a substring is in a string. We can count how many of the substring we have in our string. We can check if the string ends with a substring. It does this. These don't have to be single character strings. These could be multi-character strings, and we can try to find the leftmost substring in our string, and find would return -1 if the substring is not found. Actually, there is another call which the book doesn't mention here, at least, but I will mention it here below or to the side, and that one is index. Let's see if I can fix this. So index works a little differently. In the case of index, it works exactly like find, except when we have when we don't have the substring in the string, index actually returns, erases an error. So we should be using index when we absolutely make sure that the substring is actually in the string. So find returns the lowest index or the leftmost index where the substring begins. So find is safe to use, even if the substring doesn't exist. It's not a problem, but index would return an error. So starts with, and then we have ends with, so we can check all these things. So I will give you guys examples of this. Actually, let me switch to my notes and enter some code there, but I'm going to talk about some other things. So let's see. Okay, let's move. Actually, these are quite simple, so I'll go on. Then we can check if string contains is alphanumeric, which means alphabetic, and numeric, which means it's made up of strict letters, A through Z uppercase, and digits, which means 0 through 9. We can check if a string is made up of characters that are alphabetic only. So those are just alphabetic characters, which means only letters. We can check for digits. So if it has only values 0 through 9, we can check if the string is made up of lowercase letters, if we have any spaces, if the string contains nothing but spaces. It can be multiple kinds of spaces, like new lines, tabs, and just regular blanks. and we can check whether the string is in uppercase. So when checking for strings, we can, if the two strings look identical, then they will be equal. So equal will return true. If they don't look identical, and you can see here that the second John is written with a lowercase, then they will not be equal. John with lowercase j being less than, no, because lowercase j has a higher ordinal value than uppercase j. So as soon as we check the j's, we decide that lowercase John is not less than uppercase John. So we can check if lowercase John is in John Johnson, no, because they're written differently. And we can check whether HO is in the name. It's true because I'm sorry, is not in the name, so we have no HO, so that would return true. We can count how many times we have O's. We have John and Johnson. So we have OH, substring OH twice. Finding OH would get us 1 because it's 0 and 1, so right there it starts. And HO would get us -1. And check if it starts with John, whether it has space, alphanumeric, and all that. So you can check if 1729 is made up of digits, true. If -1729 is made up of digits, no, because my negative sign or dash is not actually a digit. Now there is actually the other version of find that the book doesn't mention here, at least, and that one is called rfind. So if you use rfind, it's going to start looking from the right end of the string. So this is reverse add, reverse find. So it'll start from the end of the string. So you can try actually on the same string to do rfind, and you should get the index for this value, for this O instead of this one. So you should run this example on your own and then make sure that you understand what's happening here, because it's just simply running all these examples that we just mentioned. So let me see where we are here actually. All right. So how do we determine if how many blank spaces we have in a string? We're going to do this thing as an exercise in just a little while. So we can take a look at these other ones, because these are self-check exercises. I think there are answers in the back of the chapter, so we can double check. So input validation is another critical thing. So when users enter values, you need to make sure that they are acceptable, and if they're not acceptable, we return an error message and ask the user to re-enter the value if that's the case. In some cases, of course, like with drop-down menus and those kinds of controlled input cases, we simply make it impossible for the user to enter something invalid. But when the user is free to enter anything that he or she wants, then we can be getting values that are improper. So in the case, we need to take care of it. Sometimes the value is fine, but it's not in the acceptable range. For example, if you say enter the day, and somebody enters to 35, there are no days that are the 35th day in any month. If we are entering years, there is no negative year. If you are entering distances, there are no negative distances and things like that. So you need to make sure of that. So this part of the book is talking about that. So we need to make sure. So we need to run checks on our input values to make sure that they are all proper. So if you accept a two-letter designation of a state in the United States, you need to make sure that it's one of those acceptable ones, and it's not something that somebody just made up. For example, there is no KX, for example. There is KY for Kentucky, but there is no KX. So if you accept that, then your program will fail or do something funny, possibly. So you need to make sure that as you enter as you accept input from the user, that input is actually correct in every way. So Well, we can actually exit programs using exit. We have to import exit from the system module, and then we just call it. And then we have the graphics window program. This is actually a little module that's provided to us by the author. So we're going to take a look at that separately because I need to show you how you can set this up. So we'll do interesting things with this possibly because it's a nice teaching tool, and it's actually a really nice learning tool. So something about AI, I'd like you guys to read these things because they're very useful and very informative. I'm not going to take the time right now to go through this myself, but it's nice to read and it's very informative. It's stuff that you have to know, not necessarily for exams, but for your own knowledge. So, so we have exercises here which we can come back to regarding the graphics package. So I want to just stay with the fundamentals here. So then the book talks about pulling graphs. I'm not going to do this right now. It's rather simple if you follow the instructions here, but it's something that would be nice for you to know. But at this, I'm not going to be holding you responsible for these. I may be showing you, or I may use these things as examples from time to time, because visualization is actually really useful, and the more you know about it, the better off you are. So in that sense, actually, it's really nice that the book talks about it. But since we have a lot of stuff to cover, actually, I'm going to skip through these things right now. So we have different kinds of colors we can pick for all kinds of elements like lines and markers and all that. And we have different kinds of line styles we can use to draw our graphs. And then we have different marker styles. So it makes things really easy to use. I'm skipping through these things. Sorry, we don't have smooth scrolling here, but so that actually concludes the chapter. So before I get to the next chapter, which is about looping or repetition, let me remind you that I will be giving you a bunch of exercises for you to work, and you guys have to be keeping yourselves really busy until we can get back to school, and we don't know exactly how things are going to work out. So we don't want to miss your opportunity for learning just because we don't have school right now. So there's a lot of challenging exercises here that I'm going to assign you guys as homework, but I'm going to start to refer to these things by their name rather than rewriting them myself, which takes longer. So I'm just going to tell you guys to do, like, for example, exercise P3.29 and so on, so that you can refer back to the book. I encourage you to keep this book right next to you, keep reading it, keep doing the exercises, keep repeating the exercises inside, solving other exercises that I have not asked you to solve, because I cannot ask you to solve everything. It's a really nice book, and it's a really extensive book, so you should take advantage of it now that we are using it, unlike in previous semesters actually. So a lot of exercises, which is nice. So next chapter is about loops, but I'm going to switch to my notes in just a second here, and then I'm going to talk about a list of things about chapter 3. So again, this is already on the Dropbox site. So I have this thing here, so I can actually insert images and such. So we talked about these things. So relational operators are these, as we mentioned, and then never use equal to check equality on floating point numbers. And we talked about string comparison, and I actually even added the idea of tuple comparisons, which works exactly the same way as a string comparison. It means element by element. So here we also showed that the ordinal value of C is not the same thing as the ordinal value of uppercase C. They are different. So when we compare these two, we're going to see that actually in this case that lowercase abc is not less than, because the A value and B value are identical, but C value is not. So the lowercase c has a higher ordinal value, so it's not less than. 67 because it's 99. Then we have logical operators that are based upon nothing but three operators, and, or, and not. So if you prepare actually a logic table for the relationship A and B, we're going to have to list all possible combinations of A and B. So we have false, 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 true, true, false, true, true. I put in ones and zeros, so 0 meaning false, 1 meaning true in this example. So we'll have false, 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 true, because we're going to get true only when everything is true. So whether you have 2 or 3 or 4 doesn't matter actually. So if you have true and true and true and true, that's the only time you're going to get a true result. As long as you have a single false, doesn't matter how many truths you have, you'll get false. So if we reverse the A and B relationship, we get NAND relationship, which means not AND, which is exactly the inverse of what AND produces. So we have the same table here. So we have these values reversed, as you can tell. False, false, false becomes true, true, true. And the only true value becomes false in NAND, or not AND. Then we have another interesting operator called XOR, or exclusive OR. Now, my point here is that I want to show you that everything else, like I said at the beginning, just written here, that are logical operations are actually created out of these three fundamental logical operators. So XOR is a good example because XOR, in short, is written like this. So this is A XOR B, and it's written with a symbol like this, a plus in a circle. But the way it's implemented actually in logic is like this. And it's, as you can tell, these are NOT gates, these are AND gates, and this is an OR gate. So this is an OR relationship, AND relationship, and NOT relationship. So if you take a look at the upper part, we have A coming in, and we have the not A, B inverted, or not B coming in, and these are ended. So we have A and then B not. And on the bottom we have B coming in straight, and we have A inverted. So we have A not B. And then all we're going to do is just take these two and then OR them. So we have A and not B, or not A and B. And that's what we have with XOR. That's what XOR actually does. So if we take a look at, so I'm going to take all these pieces. We're going to take AB, not A, not B, and then A, not B, not AB, and list them like this. And then finally, OR these two columns to get XOR, we get the following. So for false, false, we get false. For false, true, we get true. True, false, we get true. True, true, we get false. Well, we can make the observation here, and that's actually the meaning of XOR, is that when the two values are different, we get true. When they're identical, we get false. So that's why when A and B were both false, we got false. When A and B were true, we got true. And in the other two cases, when that they were different, we got true. That's exactly what XOR does. Now we can write a program actually to generate this table, but since we're not have not yet discussed how we can do repetitions, we're going to just do this thing one at a time. So I'm going to set up this format with 6 spaces as a string, and then I'm just going to be putting in the, so I'm going to have the A and B value here, and I'm going to have the result here. So, but I just want to also start with a title, so I'm just going to put AB, A XOR B, and then I'm just going to put a line below so you can see how I printed that. Then I have 1, 2, 3, 4 cases here. So I have false, 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 true, true, false, true, true. And I'm using tuple assignment here, which makes my life easy. So I have A, B matching false, false. So A will be false, B will be false, or B will be false. Here A will be false, B will be true, and so on. And then what I do is I just simply generate the parts that I need. So since I have A and B, I need to generate A naught, B naught, or not B, or not A. I could have written like that, but so I just take I just reverse them, not A, not B. And I do my XOR following exactly the formula. A not B, or not A, B. So you will see here A and not B, or A not and B. So I just get my result and then simply print it using the same format as above. So I just do it for all the 4 cases and I get the following. So I end up, if I run this thing, you'll see that it actually generates for me the exact table that I had above. False, false is false, true, true is false also, because they're identical. The A and B values are identical. So when A and B values are different, so you have false, true, or true, false, I get a true. So we ended up writing a little duplicate code, but we're going to look into how we can actually do this thing a whole lot shorter than this and not have to repeat the same code pretty much. But that's going to be the subject of the next chapter anyway. So I talk about exactly. So I gave you. So this is just a little more explanation, but I should give you some extra reading here and all that. Then we have something that the book doesn't cover, but I wanted to cover it, and it's a bit more complicated, but it's something that you also have to know. These are bitwise operators. Bitwise operators act on the individual bits of an integer valued entity. The value could be negative or positive, and we'll see there's a little complication, especially with negative values, but it's just the way it is, and we just have to learn the rules and understand the logic and then manage to handle these. So when we write x ampersand y, this means bitwise end. So we're bitwise ending the bits of x and y. And when we have the vertical bar, it's we are bitwise ORing the bits in x and y. When we have tilde x, we are complementing or taking what's called one's complement of x, which means we just reverse the bits. Bitwise XOR is x caret y, and then we have two shifts, shifting to the right and shifting to the left. So let's take a look at bitwise airing and bitwise ORing. So let's take a look at x and y. So we have 9 and 5. So we just take the bitwise end these two values and bitwise OR these values, and we print them out and we get 1 and 13. So how do we get these? So let's just print these things in 4-digit binary format so we can see what we have. So x being 9, y being 5. So this is 9, this is 8, and it's a 1, and this is a 4, and this is a 1. So you have 5 and 9. So when you end these bits, we have 1, 0, 0. 0 and 0 ended with 1 is 0, 0, 0, 0. So we have 1 and 1, 1. So that's why we got 1 when we did the ending. When we OR, we have 1, 0, 1, 0, 1 becomes 1, 0, 0 will be 0, 1, 1 will become 1. So this is 8, 4 plus 1. That's a 13. So that's why we got 13. It's really that simple. Bitwise complementing is about reversing the bits. So let's take 9 and reverse its bits. So 9 is 1 8 and a 1. So we get 6. So so that's what it looks like at least. And let's see here. But let's just check. So when we take the complement of x, it turns out we don't get 6. We get minus 10. Why is that? Now, this is what I mean actually when we talk about especially negative values. And we have done something when we reverse the bits, but we need to realize what that is actually. So we need to represent these things as 8-bit integers to see what's really going on. So here is 9, expressed in 8 bits. Okay. So we just write it out like this, and then when you reverse the bits, we get this value. So if you look at it to the right, it looks like we get a 6, but we got all these ones to the left. So no matter how long this value is actually when represented internally, we're going to have bits to the left that are going to be zeros because we get 6. And all those bits, as you see here, will be turned into ones when we reverse the bits. Well, with signed integers, actually, the leftmost bit is the sign bit, which tells you whether you have a negative value or a positive value. Since this is this value, this most significant value actually in this case is a 1, that means we get a negative value. Well, but we cannot read off negative values just like that and say this is whatever that value is. Cannot just take these bits and say, this is a, this particular value negated. It doesn't work like that. We have something called 2's complement. Actually, all values, positive or negative, are represented in 2's complement, which means we reverse the bits of the value and then add 1. But with negative values, we get a slightly different representation. And with positive values, we get exactly the same thing. But with negative values, we get a different representation. So we cannot immediately be able to. We can actually once we learn what's going on. But when we look at this value, it's a negative value. But what is it a negative of actually? So what we need to do to reverse this value into a positive version of it, so that we can tell what negative value this actually represents, we have to reverse its bits and add 1 to it. So let's just write it out. So here's our value. We didn't negate it, so I just put this bar over the value so that I indicate that we are reversing the values, reversing the bits. So we got 0, 0, 0, 1, 0, 0, 1. And the above value is 9 decimal. So when we add to this thing, we get 10. And that's actually meaning that we had minus 10. So when we have complement of 9, we got minus 10. So let's try the same thing with a negative value. So we have minus 14. When we take the complement, we get 13. Why do we have that? But first of all, we need to actually represent 14 in 2's complement. To do that, we start with the positive version of the value, which is 14. Then we reverse the bits, and then we add 1 to that. So here is 14, 1, 8, 1, 4, 1, 2. That makes 14. This is 14 decimal, in binary. So when you reverse the bits, we get the following. And when we add 1 to this, we get this value, 1, 1, 1, 0, 0, 1, 0. So this is how minus 14 will be represented in computer's memory. Let's call this value v. So now we're going to do the complement. The complement is really easy. It's 1's complement. All we do is just take the bits, reverse them all. So here's the value that we start with. This is minus 14 in memory. And when we reverse the bits, we get this. So when we get this, to take a look at this and take a look at what this value is, this is an 8 plus 4 and a 1. So that's 13. So that's what we got here.